So we're now going to look at the reciprocal trig graphs. These are different from the inverses. These are 1 over sine, 1 over cos, and 1 over tan. And they have special names. So we have 1 over sine is called cosec, or it's technically called cosecant, but cosec is the abbreviation we tend to use. Then we have 1 over cos, which is sec x or secant, but again, we normally just use sec. And then 1 over tan is cot x, which you could also write as cos over sine, and that is because if we think about it, we know that tan x, you can write in terms of sine and cos as sine x over cos x. So you can also write cot as cos over sine. That will help us later when you're asked to show that one algebraic expression with trig in is equal to another expression with trig in. So it's used a lot in those kind of questions. And you might be thinking, how on earth do you remember this? The trick is basically look at the third letter. So here, the S in cosec matches with the S of sine. For cos, the C of cos matches with the C of sec. And then the T of tan matches with the T of cot. So there's not much more to it than that really that can help you remember them. So we also need to know how to sketch these. So let's have a look at sketching cosec to start with. We're going to do sine x. And then on the same graph, we are going to plot y is equal to 1 over sine x, which is our cosec x. They are the same thing. So let's first of all just plot sine x. We should all know what sine x looks like. So let's think about what would happen here when we have 1 over sine x. So if we were to say, for example, let's just take this bit here where sine x is 0. So when sine x is 0, 1 over sine x will then be 1 over 0. Now, you may have tried this before on a calculator. You can't divide by 0. It doesn't work. So what's going to happen is we're actually going to have asymptotes. And anywhere that sine x equals 0, you are going to get asymptotes. We also need to think about what is going to happen when, let's look at here. So let's look at this point here. When sine x is 1. 1 over sine x being 1 is 1. So we're going to have a point here. And let's think about when sine x is minus 1. So 1 over minus 1. You can have a point here. And then it's going to be the same at any point where we have sine x being 1 or minus 1. So they're all points of our graph. And then let's think about what's going to happen when we veer away from 1 and 0. So I'm hoping we recognise that if we do 1 divided by a very, very small number, we get a very, very large answer out. As sine x tends towards 0, our cosec x, or our reciprocal, is actually going to go the other way, and it's going to tend off to infinity like this. And then the other side, it's going to do the same thing as x tends towards 0, sine x tends towards 0. Our cosec x is going to tend to infinity. And then it's going to do the same for the negative, but instead it would tend to negative infinity as well. So that's what our graph of cosec is going to look like. And I'll just highlight that so that's easier for you to see. So that is the graph of cosec x. I realise my axes here did not have minuses. There we go. Do the same thing for cos and tan as well. So I've just sketched y is equal to cos x there. So now let's sketch 1 over cos x, which remember is sec x, the c being the third letter in. It's going to do a very similar thing to cosec x being 1 over sine, where cos is 1 and minus 1. Those points are going to touch because 1 divided by 1 and 1 divided by minus 1 get you the same thing out. And where we are at 0, that's where we're going to get asymptotes. So we're going to get asymptotes this time at 3 pi over 2 and pi over 2. So there are asymptotes, and then we know that we start at the points where it's 1 and minus 1, and then we veer off sort of towards where those asymptotes are as sine x, or sorry, cos x in this case, it's very, very, very small. 1 over cos x or sec x is going to get very, 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 very big. So that is what sec x is going to look like. Okay, so this is the graph of y is equal to tan x. So now I want to draw 1 over tan or cot x. So I've got tan here. So let's think our asymptotes are now going to change. I'm actually going to draw this underneath as where tan x is 0, that's where we're going to get asymptotes. So now we're going to get asymptotes at intervals of pi, but this time it'll be like 0, it will be pi, it will be 2 pi. That is where our asymptotes are going to go. And then basically it's sort of going to go the other way instead. So that's where my asymptote is going to be, where tan x is equal to 0. Then if we think about starting to draw that, well, we know when we're at 0 here we're a little bit above 0, but we're still tiny. So that means here, and our tan x is really small, our 1 over tan is going to be really large. It's going to go here. And then what's actually going to do is we're just going to then follow the curve and then go to the other asymptote. We're actually going to go through minus 3 over 2. We're going to go through there going to go through the axis there and so on. It's sort of going to basically look like the graph going backwards, basically. And that is what our graph of cot x is going to look like. So if you notice here, we're 0 here where it's pi over 2. So that's where our asymptotes used to be. So sort of where we were at 0 and tan is now our asymptote for cot. And where we had an asymptote on tan, we now go through 0 at cot. So now let's have a look at this question. So it says sketch -1 plus sec 2x in the interval 0 to 360. So with the graph transformations, first of all, I'm going to rewrite it to a form that I like. So let's think about the transformation that's happening. So this 2x, that will be a stretch of scale factor 1/2 because it's x, it's the opposite, and then that'll be in x. And then the -1 is a translation. That will be -1 in y. So that's, first of all, let's think about what sec looks like first. So that's sec x. So now let's think about this transformation sec 2x. So we know 2x is a stretch of 1/2, which means that this is going to squish. So instead of taking 360 degrees to do one sort of period, it'll take 180. So we're basically just going to have a repeat of that. So let's have a go at sketching that. So this is where, especially for graphs I'm a bit more unfamiliar with, I like to have it here to remind me. So I did have an asymptote at 90. It's now going to be at 45 here. So halfway between 90 and 180. And let's just draw one period first. So we know it's going to start 1, and it's going to shoot off like that. And then here we would be at 1 at 90 now. And then it's going to shoot off on either side. And then here at 180, it would hit 1 again. And we know it would come from up there. So that is one period, if you like. We're going to have another asymptote between our 180 and 270 here. And then we're going to have another asymptote between 270 and 360 here. So this is going to carry on and look like this. And then at 270, we'd be at 1 again. And we know it then turned off either side like that. And then at 360, we'd be at 1 again, and it would have come from up here like so. So that would be y is equal to sec of 2x. So now let's finally just do the translation of -1. So everything's going to shift downwards here. So where I was at 1, I'm now going to be at 0. And where I was at 1 here, I'm now going to be at -2. First of all, the asymptote's going to be the same place. Then where I started at 1 here, I'm now starting at 0. So that's just going to do that. And then remember, it's still going to carry on because it's shooting off basically to infinity. And then when we were at -1, we're now going to be down here at -2. So at 90, we'd be touching there. And then we'd be trailing off like so. Then at 180, again, we'd be touching at 0, not 1, because we've gone down by 1. And then at 270, we'd be back at -2, like so. And then 360, we'd be at 0 again. And that's it. And that is the transformation of -1 plus sec 2x. So let's now have a look at this question. So it's first of all asked us to sketch the graph of 4 cosec x. So let's have a go at that. Now just be careful here because it's between -pi and pi, so make sure you've got your range correct. Let's just draw what sine looks like in that range. So then let's think about what cosec would look like. So we're going to have our asymptotes wherever we have sine x being 0. And then we know at 1 and -1, we're going to have values, and then they're going to go off like so, nearing our asymptotes. 4 cosec x, that's going to be a stretch of scale factor 4 in y. The key points here on our y-axis are only 1 and minus 1. So times those by 4, it's now going to be 4 and minus 4. So what I can do here is I can be quite lazy about this. And I'm just going to rewrite those as minus 4 and 4. So now on the same axis, it wants me to sketch y is equal to x. So we know it's going to pass through 0, 0. So pi over 2 is roughly 1.57. So I'm going to say 1.57 is about here. So I'm going to call pi over 2 about here. And then same here. So I'd say halfway here is about 2. I'm going to go a little bit in here and say that's minus pi over 2. You only need 2 coordinates, really, 0, 0, and one of those just to help you plot that. So I'm going to go here. And obviously this is quite rough, but here and here. So that is y is equal to x. So if you sketch that with any sort of accuracy, we can see that those two graphs they don't intersect at all. So this brings us to part C, which says state the number of solutions to this equation here. So 4 cosec x minus x is 0. Now, hopefully we can see it's got to be something to do with what we just done. And a lot of these kind of questions, they lead on from each other. So we've drawn the graphs of y is equal to 4 cosec x and y is equal to x. Well, let's make those equal to each other. 4 cosec x is equal to x, and hope we can see now, if we subtract that x, it's going to give us this thing here. So 4 cosec x minus x is 0. So basically, we are trying to find, if we want to know the number of solutions, we need to state the number of intersections between those lines. For 4 cosec x and y equals x equal each other, they have to have some form of intersection point on the line. So as we can see, they have no intersection points. So we can say there are no points of intersection. So there are no solutions for our range at all. So when x is between minus pi over pi. So I can also use my calculator to just check that. So I've just on here done 4 over sine x, which is 4 cosec x, between minus pi and pi, because that's our domain, and then y is equal to x. So if I draw that, I can see that solution there. So I can see here's my cosec x, here's y equals x. They don't intersect each other, which is what we sketched. There's a bit more accurate than mine.